Hey, welcome back. We're going to look at a second example in section 4.1. So let's just get started here. You can check out the example. We're supposed to find the minimum vertical distance between the graphs of the equation y equals x squared plus 1 and y equals x minus x squared. All right. So we'll begin again by trying to understand the problem. You're going to have to do this, at your own pace, but I've already generated a graph. This is asking me about minimum vertical distance between graphs. And so the first thing I did was generate a graph of these couple of these functions. So I've got the x squared plus 1 drawn in red there and the x minus x squared drawn in blue. They're both parabolic functions. And then I want to understand, well, what is this problem talking about? The vertical distance. Yeah, so it's asking me for the minimum vertical distance. So what do I mean by vertical distance between 2 points on a graph? Vertical distance means that they have the same x coordinate. They have the same x coordinate. I've drawn 3 different vertical distance line segments here. Yeah, so I'm drawing lines parallel to the y-axis. Lines parallel to the y-axis have a constant x coordinate. The distance between any 2 points on such a line would be called a vertical distance. Okay, so that's just kind of understanding what the nomenclature in the problem is talking about. So it's asking me for the distance between points that look like x comma x squared plus 1. Those are up here on the graph of the parabola x squared plus 1. Yeah, and x comma x minus x squared. Those points are down here on the parabola y equals x minus x squared. So the problem is asking me for all values of x, if you choose the 2 points on those graphs, you get some vertical distance. What's the smallest it could be? This picture kind of indicates that it should be somewhere, I don't know, in this region somewhere, yeah? Because these line segments, it looks to me like somewhere in there would be the smallest vertical distance. There is no biggest vertical distance, yeah? If you just let x increase without bound, these vertical distances are going to get longer and longer and longer. So there's no maximum vertical distance between these 2 graphs. I'm going to ask you to think about a slight twist on this in the reflection problem for this section, but we're asked to find the minimum vertical distance. Okay, so I feel like I understand the problem. You give me an x, and that x determines 2 points, one on the red curve, one on the blue curve, and I want to find the distance between those 2 points. That's my objective function. We don't need to use the distance formula here because if you're finding the distance between 2 points, each of which have the same x coordinate, then the distance is just the difference in the y coordinates. And watch carefully when I do this, you subtract the smaller y coordinate from the bigger y coordinate. Yeah. So why would I say that one on top is bigger? Y gets bigger in the up direction in the picture. So those are bigger values of y up there. If you want to get the distance between 2 numbers, you always have to subtract the smaller one from the bigger one. Okay, so that's how we're going to write down our objective function. I'm going to take that bigger y coordinate, that's the x squared plus 1, and I'm going to subtract from it the smaller y coordinate, that's the x minus x squared. Okay, this is for a given value of x. Notice when I subtract a quantity like x minus x squared, I use parentheses because I need to subtract the whole thing. It's a very common sign error. Without these parentheses that I've highlighted with the red laser pointer, then I'm only going to subtract the x, not the x squared, and I'll get a sign error. All right, you can check my algebra that v simplifies into that quadratic polynomial, and it's important to understand in these optimization problems what the domain is. This value of x could be any number on the x-axis, okay? So our domain is the minus infinity to infinity. Okay, now it's kind of downhill. That's kind of the work in these applied optimization problems. Once you've got your objective function and you know its domain, you unleash section 4.3 on it. I take that objective function's derivative. Derivative of 2x squared minus x plus 1 is 4x minus 1. 4x minus 1 has no discontinuities. It's defined for all x, so I set it equal to 0. Find my critical values, and I see that there's exactly one critical value. One critical value. So if it gives me an extrema, that extrema is going to be global because there's only one. How do we see what kind of extrema it is? Well, if you want to use the first derivative test, the first derivative test says that you make a sign diagram for the first derivative. To keep these videos shorter, I've gone ahead and done it. I hope you check all this stuff. On your homework problems, you're going to need to fill in these signs yourself. On your exams, fill in these signs yourself. So stop the video here for a second and make sure that you also agree that this first derivative is negative when x is less than a quarter. It's positive when x is greater than a quarter. So the first derivative test, what's the conclusion from it? This function was decreasing and then increasing. So we have a local minimum. That local minimum has to be global, again, because it's the only critical point. All right, and now, again, just to be super careful about the question, I don't mean to be obnoxious and scroll too much here, but the question was, find the minimum vertical distance. So I'm going to be kind of picky about this, because if I asked you this question and you told me the answer is minus a quarter, I would say, well, I think you did everything right, but you didn't answer the question I asked. I asked for the minimum vertical distance. X equals 1/4 isn't the minimum vertical distance. X equals 1/4 is where the minimum vertical distance happens. If you want the minimum vertical distance, you have to take that x equals 1/4 and plug it back into your distance function. So again, I'll let you check my math here, but when you evaluate v at 1/4, you get 7/8. All right, so here's the answer to my question. The minimum vertical distance is 7/8. That's the sentence that answers the question. If you want to add some more relevant information, that distance occurs when x is equal to a quarter. So if we went back to our graph, I know I'm doing a lot of scrolling here, but if we went back to our graph, that minimum vertical distance segment looks like it's happening somewhere around x equals a quarter. I don't have the scale on the axis here, but to my eye, it looks like that minimum vertical distance would be right in there somewhere. Slightly positive value of x. You make x a little less than that, the green line gets longer. You make it bigger than that, the green line gets longer. All right, that's the end of this example. I want to just point out that there's an alternative to the first derivative test. I don't use it a lot. It's not in my repertoire. I like that sign diagram method. But if you don't, when you're trying to classify an extrema, you can always use the second derivative test as well. So let me just remind you how it works here in this example. We're at the stage where we know x equals a quarter is a critical point. So then what do? You plug that critical point into the second derivative. Maybe you remember from up above that the first derivative, I'll just remind you here, the first derivative of this function was 4x minus 1. So its second derivative is just 4. It's a constant. So when you evaluate the second derivative at your critical point, you get a positive number. Positive number means the graph is concave up there. And if you're concave up at an extrema, that extrema has to be a local minimum. So if you don't like the sign diagrams, you can always compute the second derivative and classify the extrema like that as well. All right, so there's example 2. Thanks for listening.